Right now, while you are reading this, your body is quietly dissolving. Not slowly, not metaphorically. Right now, at this exact second, the surface of your skin is being chemically dismantled, and the culprit is something you have touched 1,000 times today without a second thought. Pick up any coin. Hold it for 10 seconds, then bring your fingers close and breathe in. That smell. Sharp, cold, slightly alarming, like old blood or wet stone. Most people assume they are smelling the coin. They are wrong. Coins do not release that scent on their own. Leave one on a table for a year and press your nose to it. Nothing. But the moment your skin makes contact, something changes. What you are actually inhaling is a cloud of breakdown products from your own body. The oils on your fingertips, the outermost layer of your biological chemistry, are being catalyzed into volatile compounds by a single element acting as a chemical trigger. You are smelling your own surface being taken apart, molecule by molecule, in real time. This is not a minor curiosity. This is your biology sounding an alarm it has been sounding for millions of years. And here is what is strange. Your body does not react this way to silver. It does not react this way to copper at the same intensity. It does not react this way to gold. But this one element, sitting in the 26th position on the periodic table, triggers an immediate, involuntary chemical response the instant it contacts living tissue. Something deep in your cellular architecture recognizes it, not as a building material, not as a tool, as a threat. Think about what that actually means. Somewhere in the evolutionary history of every vertebrate alive today, this element made enough of an impression to leave a permanent chemical warning system in the body. That is not an accident. Threats do not get encoded into biology by accident. They get encoded because something happened. Something repeated. Something that cost enough lives, over enough generations, that the body decided it was cheaper to just always be afraid. And the strangest part of all is that this same element, the one your skin flinches away from, the one that triggers your olfactory system into immediate alarm, is also the thing keeping you alive right now. It is inside you. It has always been inside you. Roughly the weight of a small paperclip distributed through every blood vessel in your body, doing the most critical job in your entire biology. Carrying oxygen, keeping your brain lit up, keeping your muscles moving, keeping you here reading this. So which is it? A poison or a lifeline? A threat or a foundation? The answer, as it turns out, is both. And the story of how that happened is one of the most unsettling things I have ever learned about the physical world we live in, because it does not start in a laboratory or a history book. It starts about 4 billion years before either of those things existed, at a moment when life itself was still figuring out the most basic rules of survival. But before we get there, I need you to hold one idea in your mind. The alarm your body just sounded when you held that coin. That instinct, that chemical whisper of danger. It is not irrational, it is ancient, and it is pointing at something real. If you find this kind of story as fascinating as I do me a favor and subscribe and leave a like. It genuinely helps this channel keep going, and there is so much more of this to explore together. So, 4 billion years ago, no continents, no oceans as we know them, no atmosphere worth breathing. Just a planet that was essentially a churning, half-molten chaos of rock and gas and chemistry with nowhere in particular to go. And in that chaos, something began. Not life yet, just the slow, patient work of molecules finding combinations that lasted longer than the ones before them. Chemistry, experimenting with itself in the dark. At some point in that long experiment, something remarkable happened. A molecule figured out how to move oxygen, not produce it, not destroy it, just grab it from one place and carry it to another. That ability, the ability to transport oxygen through a liquid medium, turned out to be one of the most important tricks in the entire history of biology. Because once you can move oxygen efficiently, you can build bodies that burn energy fast. You can build muscles that respond in milliseconds. You can build a brain that stays hot and active and hungry for input. But moving oxygen is harder than it sounds. You need something with a very specific chemical personality. Something that grabs oxygen tightly enough to hold it during transport, but loosely enough to release it on arrival. Something with the right atomic structure to make that bond reversible on demand. Nature tried several solutions. Some of them are still running today. Certain mollusks, certain arthropods, some creatures that never left the ocean environment, they solved the problem with copper. Their transport molecule built around a copper atom works quietly, steadily, without drama. It does the job. Their blood runs a pale blue-green, the color of verdigris on old bronze, and it has kept those lineages alive for hundreds of millions of years. Copper is not a bad answer. It is actually a quite elegant one. But the ancestors of every vertebrate on this planet, every fish, every reptile, every bird, every mammal, every human who has ever lived, they made a different choice. Or rather, evolution made it for them, because it turned out to be faster, more powerful, more efficient at high metabolic rates. They built their oxygen transport molecule around iron. And that single decision, made in the deep prehistory of complex life, changed everything about what we are and what we are capable of. The molecule that resulted is called hemoglobin. You already know the name, but what you probably have not thought about is what hemoglobin actually is from a structural standpoint. It is a cage, a precisely engineered protein cage, built by your DNA to specifications that have barely changed in hundreds of millions of years. And at the center of that cage sits a single iron atom, locked in, controlled, prevented from touching anything it should not touch. Because if it ever got loose, if a free iron atom ever escaped that cage and entered your cell in an unbound state, it would immediately begin destroying everything around it. It would react with the hydrogen peroxide that your own metabolism produces as a byproduct of breathing, and it would generate what chemists call a hydroxyl radical. This is one of the most destructive particles your body can encounter. It tears through DNA. It punches holes in cell membranes. It oxidizes proteins until they stop functioning. A single free iron atom in the wrong place behaves less like a building block and more like something that has decided to take the whole structure apart from the inside. Your body knows this. It spends enormous resources every single day keeping that iron locked up, tagged, monitored, and stored in specialized protein containers when it is not actively being used. When bacteria invade your body, the very first thing your immune system does is hide the iron. It pulls it out of circulation and locks it away, because bacteria need iron to reproduce, and your body would rather make itself anemic than hand over the fuel. Anemia during infection is not a malfunction. It is a deliberate strategy. A scorched earth response run automatically without your permission or awareness. So here we are, carrying inside us a substance that our skin tries to warn us about the moment it touches us from the outside. A substance so reactive and dangerous that our entire internal biology is organized around keeping it contained. And yet, we cannot live without it. Remove the iron from your blood, and you have minutes, not hours. It is the engine and the threat at the same time, running side by side inside the same molecule, inside the same cell, inside the same body, that is, right now, doing everything it can to keep the balance from tipping. That balance, it turns out, is a lot more precarious than any of us were taught to believe. And it has been precarious since long before the first human ever picked up a piece of metal and decided to make something with it. Everything you were taught about the rise of iron civilization is wrong. Not slightly wrong, not missing a few nuances. Completely, fundamentally wrong. And the truth is so much darker than the version in the history books that once you hear it, you cannot go back to the comfortable story. Here is what actually happened. There was a moment in human history when the best metallurgists on the planet were working with a material so superior to iron that the comparison is almost embarrassing. It was harder, it held a sharper edge, it did not corrode in humid air, it could be cast into complex shapes with precision that iron workers of the same era could only dream about. The armies equipped with it were better armed, better protected, and more effective in the field than anything iron could produce at the time. We abandoned all of that, not because we found something better, because the world fell apart, and iron was the only thing left lying on the ground. The alloy I am talking about required two metals to produce. One of them was relatively common. The other had to travel enormous distances along trade routes that stretched across entire continents and several seas. Dozens of civilizations depended on those routes. Coastal cities, inland kingdoms, island cultures, all of them plugged into the same network, all of them receiving that rare second metal in exchange for grain, textiles, timber, or labor. The system worked for centuries. It was one of the most sophisticated trade networks the ancient world ever built. Then, within the span of roughly a single human generation, it collapsed entirely. The coastal cities burned, the inland kingdoms went silent. The ships stopped coming. Historians still argue about the exact causes, a combination of migrations, internal rebellions, droughts, and the cascading failures that follow when enough nodes in a network go dark at once. But the result was not ambiguous. The supply of that rare second metal dried up almost overnight, and without it, the superior alloy could no longer be produced. Entire military and economic systems built around that material suddenly had nothing to work with, and so people turned to iron. Not because anyone decided iron was better, because iron ore was literally everywhere. You could dig it out of hillsides in almost any region on Earth. You did not need a trade network stretching thousands of kilometers. You did not need a specific partner on the other side of a sea. You just needed fire and enough patience to deal with a metal that was, by any technical measure, a significant step down from what came before. The first iron tools and weapons were genuinely poor, softer than what they replaced, prone to bending under stress. Early written accounts from cultures in the middle of this transition describe warriors having to pause during combat to straighten their bent blades. Think about that for a moment. A soldier in the middle of a fight, kneeling on the ground, pressing a warped sword against the earth with his boot, trying to make it straight enough to keep going. That is not the image of a civilization advancing. That is the image of a civilization improvising with whatever it has left. What saved iron from being a historical footnote was an accidental discovery that took generations to fully understand. When iron absorbed small amounts of carbon during the smelting process, something unexpected happened to its internal structure. The carbon atoms wedged themselves between the iron atoms in the crystal lattice, locking the layers in place, preventing them from sliding against each other. The result was a material dramatically harder and more resilient than pure iron alone. It was not planned, it was not engineered. It was a lucky contamination that early smiths learned to reproduce by instinct before anyone understood the chemistry behind it. We call it steel, and the entire modern world is built on it. But remember what it actually is. It is iron made useful by its own impurities, a material that only works because it is not pure. There is something quietly unsettling about that, given how much we celebrate it. So the foundation of our civilization is a compromise material, made viable by accident, adopted out of desperation after a global collapse. That is the real story of the Iron Age. And the question that follows from it is one that most people never think to ask. If iron was always inferior in its pure form, if it only became powerful through contamination and imperfection, then why did ancient peoples treat it as something almost sacred? Why did they fear it? Why, in the mythologies of cultures that had never met each other, does iron appear again and again as something that came from beyond the normal world? Something that did not belong here? The answer to that starts not in a forge or a mine. It starts in the sky. And what fell out of that sky, long before any human learned to smelt ore, was so far ahead of anything earthly metallurgy could produce that the people who found it had no framework to explain it except the divine. Imagine living in a world where iron is rare, difficult to work, and consistently disappointing in its results. Your best smiths struggle to produce tools that hold an edge for more than a few uses. The metal bends, dulls, rusts. Everyone knows its limitations. And then, without warning, something falls from the sky with a sound like the earth splitting open, and where it lands, you find a stone that rings when you strike it. Heavy, dense, unlike any rock you have ever handled. And when your best craftsman works it, slowly, painstakingly, using techniques borrowed from stoneworking because he has no other frame of reference, what emerges does not behave like the iron he knows. It holds an edge with a sharpness that earthly iron cannot match. It does not corrode. Weeks pass, then months. The surface stays clean and cold and bright. Nothing in his experience explains this. Several decades ago, researchers examined a ceremonial blade recovered from the burial site of an ancient ruler. The tomb had been sealed for over 3,000 years. Every organic material inside had long since decayed. The gold objects were tarnished. But this blade, made of metal, was essentially unchanged. Its surface was still reflective. When scientists ran a detailed chemical analysis on the blade, the results pointed in one direction only. The metal contained levels of nickel and cobalt that are simply not found in ore extracted from the earth. The ratios matched, almost perfectly, the chemical signature of iron meteorites. Rocks that formed in the cores of ancient asteroids billions of years ago, before our solar system had finished assembling itself. That blade had not been made from earthly material. It had been made from a fragment of a dead world that had traveled through empty space for an unimaginable length of time before falling into human hands. The nickel content is what made it resist corrosion. Earthly iron, no matter how well smelted, cannot naturally achieve that ratio. Space did what thousands of years of human metallurgy could not. It delivered a pre-alloyed, corrosion-resistant material ready to be worked, carrying inside it a chemical composition that our most advanced modern techniques would not independently replicate for thousands of years after that blade was made. Ancient peoples had no spectrometers. They had no periodic table. But they were not unintelligent. They could observe. They could compare. And what they observed was a metal that came from outside the normal world and behaved by different rules than anything the normal world produced. Cultures across different continents independently developed the same intuition about it. It was not earthly. It was a gift or a warning from somewhere above, something that operated outside the usual boundaries of materials and time. Some traditions held that it repelled certain forces, that it created a boundary between the ordinary and the extraordinary. Others treated objects made from it as possessing a quality that set them apart from everything else in the physical world. We tend to read those beliefs as superstition now, but consider what those people were actually observing. A material that arrived from outside the planet. A material that resisted decay when everything around it crumbled. A material that carried inside it a chemical history stretching back to before the Earth itself existed. Their instinct that this thing was fundamentally different, that it came from somewhere else and played by different rules, was not wrong. It was just expressed in the only language available to them. And what that language was pointing at, without knowing it, was something that would take modern astrophysics centuries to fully describe. Because where that iron actually came from, and what it means that it ended up here, is a story that makes the blade in that ancient tomb feel like the smallest possible piece of something almost too large to look at directly. Every star in the night sky is already dead. Not metaphorically, not eventually. Right now, as you look up at that light, the object that produced it may have been gone for millions of years. What you are seeing is a ghost, a message sent from something that no longer exists. And the reason most of those stars died, the actual physical mechanism that ended them, is the same element sitting in your blood and in the railing you touched this morning. Let me take you inside a dying star. Not the small, quiet kind like our sun, which will simply swell and fade. I mean a giant. Something 20 or 30 times more massive than our sun, a furnace so large that if you placed it where our sun sits, its outer edge would extend past the orbit of several of our planets. Inside the core of something like that, the pressure and temperature are so extreme that atomic nuclei are being forced together continuously, fusing into heavier and heavier elements, releasing enormous amounts of energy with every step. That energy is what pushes outward against gravity. It is the only thing preventing the star from collapsing under its own weight in an instant. The process starts with hydrogen and moves upward through the periodic table. Hydrogen burns for millions of years. When it runs out, the core contracts, heats up further, and ignites helium. Helium burns for hundreds of thousands of years. Then carbon, then neon, then oxygen. Each stage releases less energy and burns faster than the one before it. The star is accelerating towards something, though it does not know what. By the time silicon begins to burn in the core, the star has days left. Not millions of years, not thousands, days. In those final hours, the core is generating elements at a frantic pace. Silicon fusing into sulfur, sulfur into argon, argon into calcium. The sequence climbing fast towards something inevitable. And then the furnace produces iron. The moment that happens, everything changes. Not gradually, instantly. Because iron does not release energy when it fuses with another nucleus. It absorbs energy. The reactor that has been holding the star open for millions of years suddenly flips from a source of pressure into a drain on it. The core begins consuming itself, trying to process what it has made. The outward push weakens. Gravity, which has been losing this battle for millions of years, wins in a fraction of a second. The core, roughly the size of a planet but containing the mass of an entire sun, collapses inward at a quarter of the speed of light. The outer layers of the star, still falling inward, hit that suddenly rigid core and rebound with a force that tears the entire structure apart. The explosion that follows is so bright it can briefly outshine every other star in its galaxy combined. Everything the star ever was gets thrown outward into space, and the majority of what gets scattered in that explosion is iron. That is where it comes from. The iron in that ancient ceremonial blade we talked about earlier. The iron in the red dust of distant planets. The iron in your blood. All of it was forged in the final moments of a massive star that ran out of future, and then scattered across space in the violence of its ending. Every single atom of iron anywhere in the universe has that origin. There is no other way to make it. It requires a stellar death. Now sit with that for a moment, because the story does not end with the explosion. That scattered iron drifts through space for a very long time. Cold, dark, completely inert. It travels in clouds of gas and dust that slowly, over millions of years, begin to contract under their own gravity. New stars form from those clouds. Planets form from the material left over around those stars. And on at least one of those planets, the iron that settled into the crust and the oceans and the atmosphere became part of the chemistry that eventually produced life. That transition, from stellar ash drifting in a cold vacuum to a component of a living biological system, is the most improbable journey in the known universe. And it happened to iron specifically. The element that kills stars became the engine of the most complex thing stars ever accidentally produced. Here is what I find almost impossible to hold in my head at once. The iron atom sitting inside a hemoglobin molecule in your bloodstream right now went through all of that. It was forged under pressure and temperature that no earthly process can replicate. It survived a stellar explosion. It drifted through interstellar space. It became part of a planet. It became part of geology, then chemistry, then biology, then food, then you. That atom is older than the Earth itself. It has existed in forms you cannot imagine, passed through states of matter that most people have never heard of, and it ended up here, doing the most delicate and precise job in your body, carrying oxygen from your lungs to your brain, keeping you conscious and thinking and alive in this exact moment. We talked earlier about how your body treats iron as a threat, how it locks it away, monitors it, hides it from bacteria during infection. That instinct makes more sense now. Your cells are not being irrational. They are managing something genuinely dangerous with extraordinary precision. The same atom that ended a star is being handled by a protein molecule your body builds fresh every few months, in quantities of roughly 25 trillion individual units, all simultaneously, all without your awareness or input. The scale of that operation, running continuously inside you right now, is something that should stop you cold when you really think about it. But here is the thing that changes the picture entirely. If iron is the product of stellar death, and if iron is what your blood depends on to function, then what does that make the planet itself? Because the Earth is not just lightly dusted with iron. Iron is not a trace element here. It is the dominant substance of this world at its core. And what that core is doing right now, this very second, is something that most people are completely unaware of. Something that is the only reason you are here at all to hear any of this. Without the iron beneath your feet, every single person on this planet would be dead within years. Not centuries, not generations, years. And almost nobody thinks about this fact even once in their entire life. We left off with a question. If iron is what your blood depends on, and if iron arrived here as the scattered ash of dead stars, then what is this planet actually made of at its core? And what is that core doing right now? The answer to both parts of that question is the same, and it connects everything we have talked about into something much larger than any of us were taught to consider. The Earth is not a solid rock you are standing on. That idea, the image of a firm, reliable planetary surface, is one of the most comforting illusions in human experience. What you are actually standing on is a thin, brittle shell of cooled rock floating on top of a planet that is mostly liquid and mostly iron. If you could cut the Earth open like a piece of fruit, roughly a third of its entire mass would be iron, concentrated at the center, heated to temperatures matching the surface of the sun, under pressure so extreme that the innermost part, despite being hotter than most stars ever get on their surfaces, is compressed into a solid crystal that grows about 1 millimeter per year. Surrounding that solid inner core is an ocean of liquid iron 2,000 kilometers deep, moving in slow, enormous currents driven by the rotation of the planet and the temperature difference between the core and the mantle above it. That moving liquid iron is generating something. The same physics that makes a copper wire moving through a magnetic field produce electricity works in reverse here. Moving iron, which conducts electricity, moving through a magnetic field, generates more magnetic field. The system feeds itself. The result is a planetary magnetic field that extends tens of thousands of kilometers out into space in every direction, deflecting the constant stream of charged particles that our sun fires outward continuously. That deflection is invisible. You cannot feel it. You cannot hear it. But without it, those particles would strip away our atmosphere layer by layer over geological time, the same way water pressure strips paint from a surface if you hold it there long enough. We know exactly what happens to a planet when its iron core stops moving. We have a detailed example sitting in our own solar system, close enough to observe with modern instruments. This neighboring planet was once warmer. It had a thicker atmosphere. Evidence strongly suggests it once had liquid water on its surface. Its iron core was active, and its magnetic field was real. But this planet is smaller than Earth. and smaller planets lose internal heat faster. At some point, its core cooled enough that the liquid iron slowed, the dynamo effect weakened, and the magnetic field collapsed. What followed was not dramatic. It was slow and relentless. The solar wind worked on the atmosphere for millions of years, gradually thinning it until the pressure dropped so low that liquid water could no longer exist on the surface. The water that had been there either evaporated into space or froze underground. The surface, exposed to unfiltered radiation, became sterile. The iron in the soil oxidized into a fine red dust that covers everything. That planet is now the color of dried rust, and it will stay that way forever. That is our mirror. That is the version of Earth that exists when the iron core goes quiet. And the terrifying part is that our core is also cooling. Slowly, over billions of years, but measurably. The inner solid crystal at the center grows a millimeter per year because the surrounding liquid is gradually giving up its heat. At some point in the deep future, that process will reach a threshold. The currents will slow, the magnetic field will weaken, and we will begin the same long, quiet transformation that our rusty neighbor already completed. The field has already shown signs of instability in the geological record. Magnetic reversals, where the north and south poles effectively swap positions, have happened hundreds of times in Earth's history. During a reversal, the field does not simply flip overnight. It weakens significantly first, sometimes for thousands of years, before reorganizing in the new orientation. During that weakening, the protection it provides is reduced. We have never experienced one as a technological civilization. Our entire infrastructure of power distribution, satellite communication, and navigation systems was built assuming a stable, strong magnetic field. What a significant weakening would do to that infrastructure is something researchers have modeled and discussed quietly for years, without it ever quite reaching public conversation. All of that depends on iron. The liquid iron beneath us keeping its heat, keeping its motion, keeping its currents complex and active. We live on top of a machine built from stellar ash, and that machine is the reason any of this, the biology, the civilization, the conversation you are having with this story right now, was ever possible. But here is what I keep coming back to. We built a second iron machine on top of the first one. We extracted the iron from the ground, purified it, alloyed it, shaped it, and constructed an entire civilization from it. Bridges, buildings, pipelines, the reinforcement inside every concrete structure you have ever walked through. We did all of that without fully reckoning with one fundamental fact about the material we were using. And that fact has been costing us in ways most people never connect to iron at all. Iron does not want to be steel. That sentence sounds strange, but it is chemically precise. When iron ore is smelted, the iron is forcibly separated from the oxygen it was bonded to in the ground. That separation requires enormous energy input. The resulting metal is in an unnatural high-energy state. It is, from a thermodynamic perspective, under constant tension. Every steel beam, every iron pipe, every reinforced concrete foundation ever built is in a state of permanent chemical restlessness, always pushing toward the lower energy configuration it was taken from. We call that process corrosion. But that name makes it sound like a surface problem, like something you can handle with paint or a coat of zinc. It is not a surface problem. It is a fundamental property of the material. It is physics collecting what was borrowed. The numbers behind this are genuinely staggering. Estimates from engineering and materials research consistently place the global annual cost of corrosion at around 3 to 4% of the entire world economic output. That is not a rounding error. That is a sum larger than the gross domestic product of most countries on Earth, spent every single year not building anything new, not advancing any technology, simply maintaining what already exists against the relentless chemical pressure of iron trying to return to the state it came from. Every coat of paint on every bridge, every sacrificial zinc plate on every ship hull, every anti-corrosion treatment on every pipeline carrying fuel or water. All of it is a holding action. None of it is a solution. And sometimes the holding action fails quietly, invisibly, in places no inspector thinks to look. Corrosion inside a structural element does not announce itself. It progresses in darkness, behind walls, inside concrete, underneath road surfaces, molecule by molecule, weakening cross-sections that were calculated to carry specific loads under the assumption that they would remain intact. The calculation holds until it does not. And when it stops holding, the failure is not gradual. A structure under load does not slowly bend and warn you. It reaches a threshold, and then it is simply gone. In a second, with no intermediate state between standing and fallen. Engineers who study these failures describe a consistent pattern. The corrosion was there for years before the collapse. It was advancing at a measurable rate that, if anyone had looked in the right place with the right instrument, would have been visible and quantifiable. The material was doing exactly what iron always does. It was going home. The failure was not a surprise to the physics. It was only a surprise to the people who forgot that the material they built with had somewhere it was always trying to return to. We built our world from a substance that is programmed, at the atomic level, to undo everything we make with it. And the deeper question, the one that keeps pulling at me the more I think about all of this, is whether that tendency in iron, that drive toward a specific final state, stops at the scale of a bridge or a building. Because the physics that governs a rusting iron beam does not change when you zoom out. It scales. It applies at every level of organization, from a single atom to a planet to a galaxy. And what it points toward, at the largest scale anyone has ever calculated, is something that makes the corrosion of our cities look like the most minor possible preview of a much larger ending. Every atom of gold you have ever seen or touched is slowly, inevitably, turning into iron. Not in your lifetime. Not in the lifetime of our sun. But the process has already started, and nothing in the universe can stop it. We ended the last part with a question about scale. Whether the tendency of iron to seek a final resting state stops at the level of a corroding bridge or continues outward into something much larger. The answer is that it does not stop anywhere. It goes all the way to the end of everything. And the mechanism behind it is one of the strangest and most unsettling ideas in all of modern physics. To understand it, you need to think about energy the way a physicist does. Imagine the entire landscape of matter as a physical terrain, a vast surface with hills and valleys. Every element sits at a specific elevation on that terrain. Hydrogen sits very high up, full of potential energy, ready to release enormous amounts of it through fusion. Uranium sits high on the other side, bloated and unstable, releasing energy by breaking apart. Everything on that landscape is under a kind of invisible gravitational pull, not toward the center of the Earth, but toward the lowest point on the energy surface. And that lowest point, the deepest valley in the entire landscape of matter, is iron-56. The specific isotope with 26 protons and 30 neutrons, packed together in the most stable nuclear configuration that physics permits. Everything in the universe is, in a sense, trying to get to that valley. Heavy elements want to shed mass and slide down from one side. Light elements want to fuse and climb up from the other side. Iron is already there. It has nowhere to go. It is the destination that all other matter is moving toward, whether quickly through stellar explosions or slowly through processes so gradual they make geological time look frantic. The slow process is the one that most people have never heard of, and it is the one that applies to everything that survives long enough. Quantum mechanics permits something that classical physics absolutely forbids. A particle, under certain conditions, can cross an energy barrier without having enough energy to climb over it. It simply appears on the other side. This happens constantly at the subatomic level, in radioactive decay, in the chemistry of your own cells, in the surface of the Sun. At normal temperatures and pressures, these tunneling events in atomic nuclei are extraordinarily rare. But rare is not zero. And when you multiply an extraordinarily small probability by an extraordinarily large amount of time, you eventually get certainty. Given enough time, a block of gold sitting in perfect empty space with no heat, no radiation, no external force of any kind, will rearrange its own nuclear structure, atom by atom, through quantum tunneling events, until every atom has migrated to the lowest available energy state. The gold will become iron. Not rust, not oxide, pure, cold, crystalline iron 56. The same process applies to every other element. Carbon in a diamond, silicon in a processor chip, oxygen in the air. Every atom of every substance that is not already iron is, over timescales almost beyond description, in the process of becoming iron. The universe has a drain, and everything is moving toward it, just at speeds so different that on any human timescale, the motion is completely invisible. The end point of this process has a name in theoretical astrophysics. Researchers who model the extreme long-term future of the universe call it the iron star era. By the time it arrives, all the stars will have long since burned out. All the black holes that formed from collapsed stellar remnants will have slowly evaporated through a quantum process that bleeds their mass away as faint radiation over unimaginable timescales. The universe will be dark, cold, and expanding still, with distances between any two objects so vast that light from one could never reach another in any remaining time. And drifting through that darkness will be objects made of nothing but iron. Smooth, cold, perfectly crystalline spheres, ranging from small to enormous, containing within their structure every atom that ever existed in anything, every mountain that ever stood, every ocean that ever moved, every living thing that ever grew and breathed and felt the warmth of a star, all of it compressed and rearranged into the same silent, stable, featureless lattice. No reactions occurring inside, no heat being generated, no information being processed, no events of any kind taking place, just iron in the dark for the rest of time. That is not a hypothesis. It is a mathematical projection based on known physics. The only uncertainty is the timescale, which involves numbers so large that writing them out in standard notation would require more digits than there are atoms in the observable universe. But the direction is not in question. The destination is not in question. Iron is waiting at the end of everything, and it has been waiting there since the first atom of it was forged in the first supernova billions of years before our planet existed. Now here is the part I want you to sit with, because this is where most people who encounter this information either feel a kind of crushing despair or disconnect entirely and go back to their day without really absorbing what they just heard. And I think both of those responses miss something important. Think about what the iron star era actually tells us about right now. If the natural default lowest energy state of all matter is cold and silent and inert, then everything that is currently not in that state is an exception. Every star burning in the sky is an exception. Every molecule of liquid water is an exception. Every living cell, dividing and metabolizing and responding to its environment, is a spectacular, improbable, thermodynamically costly exception. The universe in its resting state does not do any of those things. It simply is, quietly, without event or change or witness. We are not the resting state. We are the exception. We are the brief, noisy, complicated, warm, aware interval between the chaos of the early universe and the silence of the Iron Era. And that interval, measured against the timescales we have been discussing, is so vanishingly small that describing it as brief is almost comically inadequate. It is less than the blink of an eye compared to the length of the night that follows it. But here is what changes when you actually absorb that. The iron sphere, drifting in the cold dark at the end of time, does not know it is iron. It does not experience the silence around it. It does not miss what came before. It has no relationship with time at all, because nothing is happening inside it to mark the passage of time. Duration only exists where events occur, and events require energy gradients, temperature differences, chemical potential, the kinds of instability and imbalance that the universe is slowly but relentlessly smoothing out. We have all of that right now. The star above us is still burning. The iron in the core beneath us is still moving. The iron in our blood is still being loaded with oxygen and carried to our brains and released and loaded again, 60 to 100 times a minute, every minute of every day we are alive. That process is not simple. It is not cheap. It costs energy that came from food, that came from sunlight, that came from a star performing the same kind of nuclear fusion that will eventually produce iron and end. Every breath you take is one link in a chain that started in a stellar explosion billions of years ago and ends in a cold, dark sphere billions of years from now. You are not a bystander to that chain. You are the most complex and aware part of it that we know of anywhere in the observable universe. The ancient peoples who found that meteorite blade and treated it as something sacred were not being superstitious. They were responding to something real. That metal was different. It came from outside the normal world. It did not decay like the things around it. It carried inside it a history and a chemical composition that nothing earthly could replicate. Their instinct was correct, even if their explanation was not. Iron is not just a material. It is a marker. It marks the place where a star ran out of road. It marks the floor of the energy landscape that all matter is sliding toward. It marks the substance that our biology chose to power itself with, at enormous ongoing cost and risk, because the alternative was to be slower and simpler and less able to look up at the sky and ask what the lights are made of. The smell on your hands when you hold a coin is your body reacting to something it has recognized as a boundary material for millions of years. Not poisonous in the way a toxin is poisonous. Significant in a different way. A chemical signal that says, this thing is not neutral. This thing has weight in the story of matter. Your skin knows that, even if you did not until now. We began this story with a smell and a question. The smell was your own chemistry breaking down on contact with element 26. The question was why your body responds that way to something so ordinary and so familiar. The answer turned out to reach from the surface of your skin all the way to the death of stars and the end of the universe. Iron is the element that kills suns, powers blood, protects planets, and outlasts everything. It is the beginning of the end written into the periodic table, sitting quietly in position 26, waiting with a patience that makes all of human history look like a single heartbeat. The moral of everything we have covered is this: the things most worth paying attention to are rarely the ones that announce themselves. Iron does not announce itself. It sits in your pocket, in your veins, under your feet, in the sky above you, in the light of stars that are dying right now. It is the most consequential substance in the known universe, and most people go their entire lives without thinking about it once. Awareness does not change the physics, but it changes what the physics means to you. And meaning, while it lasts, is the only thing that separates us from the iron sphere at the end of time. So here is the question I want to leave you with, and I genuinely want to know your answer in the comments. If you knew with absolute certainty that everything you have ever built, everyone you have ever loved, and every thought you have ever had will eventually become part of a cold, silent iron sphere drifting in an empty universe, would that make your life feel less meaningful or more? Think about it. Write your answer below. I read every single comment. And if this story made you think about something you had never considered before, please leave a like and subscribe to the channel. It is the simplest way to make sure stories like this one keep getting made.